Okay, so we continue the topic on species of combinatorial structures and start with homework questions. The first question is to verify that the multiplication of species is associative. So if A, B and C are species, then A dot bracket B dot C is equal to A dot B dot C. So prove this or verify this. Then the second is that multiplication is commutative up to isomorphism. Okay? In the sense that if I take two structures F and G, then F dot G may not be identical to G dot F, but they are isomorphic. Then multiplication distributes over addition. So this is another homework that you want to do, like let's say C dot A plus B is equal to C dot A plus C dot B. And the fourth part is to show the following, that suppose F and G are species of structures, then the species F dot G satisfy the following, that is the exponential generating function F dot G of X is the product of the exponential generating functions of F and G, that is F of X times G of X. Similarly, for the ordinary generating function for the isomerism type structures, F dot G tilde of X is equal to F tilde of X into G tilde of X. And the cyclic index series Z F dot G of X1, X2, etc. Infinity many variables is the product of the corresponding cycle index series of for F and G. Okay, so these are the questions. And then there is a couple of more questions. The second question, second homework is to do the following. That suppose by der we denote the derangement species. We discussed this earlier. Then show that the isomerism type is counted by the series product over k greater than or equal to 1 by 1 minus x raised to k. So that is der tilde of x is equal to product k greater than or equal to 1 by 1 minus x raised to k. Third question is to show that if p to the power bracket k denotes the species of subsets of cardinality exactly k, okay, and ek denotes the species of k element sets, then show that pk is actually equal to the product of ek and e, and hence prove that the generating function, exponential generating function pk of x is actually equal to e raised to x into x raised to k by k factorial. Now we introduce a new operation called substitution. So suppose f and g are two species, such that the species g has no structures on the empty set. That means that you cannot create structures of type G from the empty set. Okay? If this is true, then we can define f of G as f composition G as follows. So given a set U, we define f of G on U as follows. Okay, so the structure f of G, putting the structure f of G on the set U, is actually taking the set U, right? Then partition the set U into non-empty parts. Then for each part, which is a small set, right, as a subset, you put a G structure. Okay, so you put G structures on each of the parts. And then considering these G structures as elements of a set, you put an F structure on these elements, right? So on the G structures. Or basically it is an F assembly of G structures. You are assembling the G structures into an F structure. Okay, so this is called the substitution. Now another way to represent this is that, like, you have this box representation of F composition G, which is basically you partition, right? You partition the set into different parts, then put G structures on each, and then on this G structures you put an F structure, right? So the same thing. So what we are saying is that partition U into non-empty sets, put G structures on each part, now put an F structure on the set of these G structures. That is, F composition G of X is equal to F of G of X. Now it should be clear why we need that G of empty set to be empty, because if that is not the case, we should be able to partition the set U to any number of parts, because you can have empty sets as sets, and on each of the empty set, if you can put a G structure, then you don't have a bound on the number of F composition G structures that you can make, because you can make as many G structures as you want using the empty set, and then once you have this, you can use that to make the F structure on this, and the set cardinality keeps on increasing, and therefore we don't want to allow that. So that's why we insist that whenever we look at the G structure, G is species G, that we cannot make. We consider only the species where the empty set is not allowed to be part of. Okay, so one can verify that the number of so the number of structures, F composition G structures on an n element set U is given by this following formula, right? If you do this, you will get summation k equal to 0 to n factorial by k factorial into n1 factorial into etc. nk factorial, where summation nk is equal to n, and each of the n's are at least 1. And at times ak into bn1 etc. bnk, product of bn1 to bnk. So this should be familiar to you, because we discussed this when we are looking at the generating functions, composition of generating functions, and it's essentially the same thing. We are just looking at in terms of species now, right? And seeing that what is happening is precisely this. Now, as an example, let us look at the species of permutation. Okay, so species of permutations, we know that permutation is basically represented by cycles, right? So you have you can decompose the elements into cycles. So any permutation is basically a collection of cycles, which is a set of cycles, right? So a set of cycles implies permutation is a set assembly of cycles, because you take cycles, right? So you take the set, you partition, put cycle structure on each of them, right? Put them together, you get a permutation, right? Because that precisely what a permutation is. And putting them together means that you're forming a set of these, right? So basically it's a set assembly of cycles. So therefore S is equal to E composition C, right? Because it's a set assembly of cycles. And which is equal to E of C, right? The substitution. And if this is true, then it follows that the exponential generating function S of x is actually equal to E of C of x. One bracket is missing. E of C of x. And we know that what is S of x? That is 1 by 1 minus x, right? And we know that E of x is e raised to x. So therefore, E of C of x is e raised to C of x. So e raised to C of x is equal to 1 by 1 minus x. And solving for c of x, we get c of x is equal to log of 1 by 1 minus x, which is minus log 1 minus x. I think this is something that we claimed earlier, so we have a proof now, right? Okay, so we can find out, using just this observation that, a permutation is basically a set of cycles. We can directly find the generating function for the cyclic permutations. One more example: a species of rotatries is given by represented by A. Okay, so A is the species of rotatries, and if you remember, X is the species of singletons, right? Then the claim is that A is actually equal to X dot E of A, right? It's the product of the singleton species into the composition of E and A, right? E is the species of sets. Right? Now, why is this? Well, just look at this following figure. That you have a root tree here, right? It's a root tree where this is the root, let's say, right? So you have a root tree, and what is the root tree like? A root tree is basically, right? So you have a root, which is a special element, right? You have a root, and then once you remove the root, what you get? If you remove this, you will get several subtrees, right? Several subtrees, and the subtrees form a set, right? So it's a set of subtrees, which is E of A, right? Each of them is a root because this main root, right, that we removed is connected to these vertices, which makes them special, right? They are connected to, therefore they are special vertices, which means that they are roots. So therefore, we get a set of rooted trees, which is E of A. But now you have separated one vertex, which is a special, which means that this vertex is a special vertex which can be thought of as neighbors of each of these roots, which makes it the new root, right? So therefore, a rooted tree is the product of a singleton with a set of rooted trees. So therefore, A is equal to x dot E of A. Now, using things like Lagrange inversion, because the generating functions for E and X, right? Using Lagrange inversion, we should be able to compute the generating function for A, which we are not covering because we are not looking at Lagrange inversion or anything in this course. We will study that in a more advanced course. Now, another example is the species of endo functions. So we denote by E and D the species of endo functions, right? So if you recall from our earlier lectures, right, on graphs, right, we came across endo functions, right? Endo functions had this nice structure that they have this kind of structure where you have lots of rooted trees, right? We had, and these rooted trees were all going like this, right? Or we have this kind of graphs, right? We have this kind of graphs where all this direction is going in, right? Because the graph of the endo function, of course, has a property that every vertex has exactly one outgoing edge, right? Which implies that we cannot have more than one cycle, right? We have exactly one cycle because uh, all the element has some outgoing edge. Therefore, we will see that there will be cycles in each of the components, and you will get something like this, right? Now, what is this? Can you see it as some kind of operation on species? That is the question, right? So the species of endo functions, can you think of it as a combination of species as a product or composition or something like that? What can you see here? Okay, so it turns out that if you look at each of these, right, this one is a rooted tree because all the arrows are going to this vertex, right? From this part. Similarly, each vertex in the cycle has this property that it is the root of some rooted tree, right? Each vertex has this property, right? Even this vertex, we have these two trees, right? It's a root of this tree and this tree, right? Or if you want to say, you can see it as this tree. And then you have this one, right? Then here you have a tree with just one vertex, right? Which is the root. Here is another tree with one vertex. So therefore, what you have is that you take a collection of rooted trees, take the roots and put the roots into cycle forms, right? Like group them together and put some cycle structure on that. And what is this? Putting them together and putting cycle structure on them, which is basically saying that I am making a permutation, right? I am looking at the permutations of the roots. So therefore, it's basically a permutation of rooted trees, right? So what we are saying is that we have permutations of rooted trees, and which is actually equal to the endo function. So therefore, we get endo function is the composition of S and A. So S composition A or S of A is the endo functions, right? The species of endo function. And as a consequence, E and D of x is equal to S of A of x. And what is A of x, we don't know, but it is going to be 1 by 1 minus A of x because S of x is 1 by 1 minus x. So if you find out what is the A of x from the earlier part using the Lagrange inversion, we can also find E and D of x using this. Look at the partitions species. Okay, species of partitions. And what is a partition? Every partition is basically a set of non-empty disjoint sets, right? So given a set, you are going to partition into non-empty disjoint sets. That is why it's called a partition, right? I mean, you cannot have two of the parts intersecting, and you don't want to have empty parts in the partition. So therefore, for us, a partition is a set of non-empty disjoint sets. Now, since the sets are going to be non-empty sets, right? We look at the species of non-empty sets, which is E plus. Right? E is the species of sets. E plus is the species of non-empty sets. Right? You just remove the first term, whatever is corresponding to. Right? Then partition species is actually a set assembly of non-empty sets because it doesn't matter what order here. So basically a set of like when you are partitioning, you are saying that okay, you have these parts u1, u2, u3, u4, u5, right? So whichever order you put them, it is going to be a partition. Now, if you remove just the first element from E of x, it's basically the first term is going to be 1 in e raised to 0 is 1, right? So the generative function for E is e raised to x, so therefore it is e raised to x, but for x equal to 0, it's basically 1, right? I mean, yeah, so not x equal to 0 for the sets on empty sets, right? There is only one empty set, so therefore e plus minus the case where you're looking at the empty set is basically e raised to x minus 1. That is the generative function for e plus, and generative function for e is e raised to x, so therefore we get e power e raised to x minus 1, which is the generative function for the partition species. So these things are, this thing shows us that the method of species can be quite convenient, right, to come up with these kind of generative functions. Where if somebody is asked to just find out the generative function for the species of partitions, it may not be as easy as this. Now, here is a proposition which I am not going to prove. This can be done in a more advanced course. that if you take the substitution, right, of f and g, then the f composition g of x, the generating function, exponential generating function, is the composition of g of x into substitution of g of x into f. So it's basically f of g of x. Okay. So we are substituting g of x for x in f of x. On the other hand, if you look at the cycle index series, the cycle index series is obtained as follows. Okay, zf composition g of x is zf of, now. So we know that zf is basically zf of x1, x2, x3, etc. Right. So for each of these, we are going to substitute as follows. X1 is substituted with the zg of x1, x2, etc. That is basically the cycle index series for G, right? Then x2 is substituted by zg of x2, x4, x6, etc. Okay. Then z3 is substituted with x3 is substituted with zg of x3, x6, x9, etc. Right. Similarly, you do for each of the xi's. Now, this kind of a substitution is called a platheistic substitution. It has a name. Again, we won't go into any further details on this, but it should be clear what we are doing here. And the claim is that this is precisely the cycle index series for the substituted species of combustion G. And from this, one can immediately deduce that f composition G of x tilde, right, is basically f composition G tilde of x is precisely ZF of substitute this with G tilde of x, substitute this with G tilde of x square, then G tilde of x cube, etc. Okay, so these are something if you are interested, you can try to see why, but it requires a little more work, and we don't want to do it in this course. Now let us talk about the derivative of a species. Okay, so given a species f, I want to look at the derivative species f dash, f prime or f dash. Okay. Now, what we know about the derivative of the generating function. Okay, so we start with the exponential generating function. Look at the derivative of that. So f prime of x, right? So you look at f of x and look at the derivative. That is d by dx of f of x, right? So what I want is that I want the generating function for the derivative species of prime to match with the derivative of the generating function of the species f. Now, from this equation, we know immediately that the cardinality of f dash of n, where like you are looking at the set 1 to n, right? Here is so basically an n element set, right? The number of structures of type f dash on this is basically f of n plus 1. From this it should be immediately clear. Now, therefore, what we want is that we want to make sure that this property holds, right? Then only the generating function here will satisfy this equation, right? We want to make sure that this number game is perfectly matched, right? So that is the number of f prime structures on a finite set U is the number of f structures on a set with one more element, because we are looking at the set with one additional element, right? So the derived species can be thought of, right? So derived species on a set U can be thought of as the species f on a set where we have one additional element, which is a special element, but then we don't have this element in our set, right? So therefore, you put an F structure on this set and then remove this, right? Or forget about this element. Then you look at only the remaining element and what kind of structure that forms. So let us look at the picture. So the F prime structure, right, on a set is basically an F structure on the set together with a new element, where the new element is discarded after making the structure F. So we define U plus as set U union a new element star, where star is an element that is not in U, right? And a canonical way to select a new element always, right? I mean, whatever your set U is given, if you want to find a new element which is not part of it, you can take the set U itself as a new element, right? And, as an element, not you are not taking the union, you are just adding U as an element of the new set, right? So U union singleton U. So this is one way to do it. I mean, we can of course do another way. That is okay. So another picture representation is the following: that an F dash structure on a set U is basically an F structure on the set U with a new element, where the new element is sitting outside. Right? You put the F structure, forget about this, right? Whatever it is doing there. So let us look at an example. Before that, maybe I will just make a remark that the new element is actually not part of the F prime structure on U, because it's never part of U. Once we add star and construct F structure, we can forget star to obtain the structure. Now, one question that may arise is that how do you define the transport of structures, right? So sigma is mapped from U to V, right? Now, we have to make sure that this sigma is not affected when we extend it, right? So we are going to extend sigma to, let's say, sigma plus, where sigma plus goes from U plus star to V plus star, right? You add star to each U and V, such that sigma plus of U is sigma of U for every U in big U, and sigma star of star is actually equal to star. So star is always mapped to star by sigma. So if you make sure that this is there, then we can easily define the transport of sigma along transport of the structure along sigma can be carried out without trouble. Now here is a nice example. So let C be the species of cyclic permutations. Okay. Now we want to look at the derivative C dash, right? C dash structure on U, let's say U is a set A, B, C, D, E, is, as we said, is a C structure on U plus a new element star, right? So basically we are defining C star as a cycle structure on A, B, C, D, E and star. So you put this structure. But now forget about star, which means that we are going to get a linear order on the elements, right? B, A, D, E and C, right? Forms stays in a linear order because it had originally a cyclic order where we removed the star, now making it just a linear order. So the derivative of C dash is the species L of linear orders. Right? So from this we can see that C prime of x is actually equal to L of x, which is 1 by 1 minus x, and therefore C of x must be integral 0 to x dx by 1 minus x, which is log of 1 by 1 minus x. Again, we obtained the same result that we proved earlier using another method, right? Using the derivative, right? One more example. So look at the derivative of the species of sets, right? E is the species of sets. So you are making the set, taking the set U, putting an E structure on the set U plus the new element star. Then you remove the element star, you get the set structure, right? You get the structure E dash, but it is again just a set without the star. But it is the set structure on U itself. So therefore, we see that E prime is actually equal to E itself. So therefore, the derivative of the generated function for E of x must be equal to e of x, the generative function for e of x itself, right? So d by dx of e prime of x equal to d by dx of e of x also, which means that e of x must be equal to e raised to x, right? That is the only function that we know whose derivative is equal to itself, right? So d by dx of e raised to x is equal to e raised to x. So we can even like show that this must happen. Now, derivative of the species of linear orders, what is that? Okay, so you take the linear order species. So therefore, you put take the set U, add a new element star, then you put a linear order on that, right? Once you put the linear order, you remove star, you will get two linear orders, right? It is basically like partitioning the set into two parts, putting an L structure on this and putting an L structure on this. Right? Therefore, it is basically the product L dot L. Therefore, L dash is equal to L into L. And this should be true because d by dx of 1 by 1 minus x is equal to 1 by 1 minus x whole square. And, L of x into L of x is also 1 by 1 minus x into 1 by 1 minus x, which is 1 by 1 minus x whole square. So this also matches. Again, a proposition without proof, the derivative satisfies the following identities. The generating function f dash of x is equal to d by dx of f of x, right? F tilde dash of x is dou by dou x1, right? Partial differential with respect to x1 of the cycle index zf substituted with x, x square, x cube, etc. Right? Then the derivative has the following cycle index series. Zf dash of x1, x2, etc. is dou by dou x1 zf of x1, x2, etc. Right. So from this, if you just substitute with x square, you will get this one naturally. So again, this we are not going to prove, but just keep it in mind that these can be rigorously proved. As a homework, prove the following. Take A to be the species of trees. Okay. Then find the derivative A dash in terms of other species. Okay. Can you represent the derivative of the species of trees in terms of some other species? Can you represent? Can you see what it is? Then show that the derivative of the composition f composition G, right, is actually equal to the derivative of f composition G product with the derivative of G dash, derivative of G dash, right? So f dash composition G dot G dash, where of course G of empty set is equal to empty. Okay, now we go to another operation which is called pointing. Now, pointing is basically, we are just taking, a structure and, we point to one of the elements just to make it as a special, right? A good example is that, given a tree, let's say, like just take any tree, right? And then you say that, okay, one of the vertices I want to make special, right? I will make it special, right? I'll just say that this vertex is now special. Or I'm just pointing to this vertex saying that, okay, this guy is the main guy, right? So, this, what is this? This is precisely a rooted tree, right? A rooted tree is a tree with a one vertex which is marked as special or pointed by, something saying that this is the root. So, the pointing of the species of trees must make a species of rooted trees. So what is pointing in the picture? So you have you have this set, right? And on this set you are selecting one of the elements and saying that that guy is special, right? So that is it, right? So you are making it as a special vertex. and you get a router structure. But what is this? We can check or we can select any of the elements as your element to be pointed, right? You can point to any of the elements, which means that there is a one-to-one correspondence between the structures on f dash f not dash, basically f point, right? F dot of u and f of u cross u, right? The Cartesian product of f of u, right? The set of all f structures on the set u with the set u itself, because for each element I can say that okay, that element is special, right? First element of u, second element of u, third element of u, each one can be associated with this, say that this is the special element. So basically there is a bijection to this f of u cross u, right? The Cartesian product. And from this, it is immediately clear that the cardinality of f dot on an element set, f dot of n, is actually n times f of n, right? Because whenever you have a structure, you have n possible ways to point it, right? It's any of the n elements of u can be marked as special. And if this is true, of course, f dot of x must satisfy the following identity, right? It must have the form that like summation n into fn, because that is the number of elements on an n element set, x raised to n by n factorial. Now, what is this? Which is basically, if you take one x outside, you will get this basically as x times d by dx of f of x, right? Because f of x is fn, x raised to n by n factorial. You take the derivative, multiply with an x, you will get this form. So therefore, it is basically x into d by dx of f. But d by dx of f of x is the generating function for f dash of x, right? And x is the generating function for the species of singletons. So therefore, you can see it as the product of the singleton species and the derivative species of x. So f dot of x is basically x dot f dash of x. And here is a pictorial representation. You want to see that f structure on the set u, where one element is marked special, is basically identical to, right? You take the element that you want to make it as special outside, okay? Then you replace that element with a new element star, put an f structure on this, right? Now forget about this particular element, right? And just replace it with this element, right? And then you will get the f structure on this, right? Or basically the f dash structure on the set minus this element, where this element is now marked special. Therefore, you will get this as a pointed structure. Now we conclude this lecture with a very nice application to count the number of label trees, and this was given by Andre Joel. And we already counted the number of label trees in our course earlier using some techniques, and then we showed that it's actually n raised to n minus 2. So we are going to prove the same thing, but now using the species. Okay. So we have a as the species of trees. Okay, species of trees. A is the species of trees. Then what we do is that we take the species of trees and apply pointing once. So once we apply pointing to species of trees, we will get the species of rooted trees, right? We already saw that if you take a tree and point to one element, you will get a rooted tree, right? So the tree A, right, becomes a rooted tree, right? So whatever tree you start with, you mark any one of the elements as root, and you get a rooted tree, right? So therefore, from the species A, you will get the species capital A, right? When I take the pointing operation, so A dot. What happens when you do the pointing once? when you point it once, if you had whatever like some number of elements in here, suppose you had n, you are looking at an n vertex tree here, then you have n different ways of pointing here, right? So from each tree you can make n new different trees. So whatever was the number here, it will be multiplied by n, right? So you will get n times as many trees when I do this pointing. We will keep track of this, right? So we have started with some number of trees. Then we say that whenever you start with an n matrix tree, after the pointing you get n times that many trees, right? Rotor trees. Then you point again, right? So where we are allowed to repeat, point to the same vertex if you want, right? You are allowed to point the same vertex again, but so we don't lose on any choice, right? So we can point again to any of this. So you mark, it's also as a second point, right? So we get doubly pointed trees, right? So you get a rooted tree where you point once more. And this new structure is called a vertebrate. So what is a vertebrate? A vertebrate is an animal with a spine. Okay. Right. So we call the species of vertebrates. So what is it in our case? So we have a tree where we have two vertices marked as special. Okay. So the first you pointed to some element, then you pointed to an element, and the first element is called the tail, and the second element is called the head. Now, of course, this can be the same because we allow repetition. So in that case, it happens to have the same tail and head. In this case, it is called a degenerative, vertebrate. But otherwise, it is non-degenerative vertebrate. So it doesn't matter. We will look at all possible vertebrates. So we look at vertebrates with one tail. The first pointing is giving you the tail, and then the second pointing gives you the head. Now, once you have a tail and head, there is, so since we are looking at trees, there is precisely one path starting from the tail to the head, right? So there is a unique way, a unique path defined on trees between any two vertices. So in particular, you have a unique path between the tail and head. Now this unique path says what? It says that I start from you, then go in this particular direction, fixed direction, and going to the head, which says that it is basically a linear order on these vertices that we are along the path. But now each vertex on the path can be thought of as a special vertex, right? It can be thought of as a special because it is part of the path itself. So I can think of this vertex and this part, whatever remains here is a rooted tree because it is a root. Then this vertex together with whatever is here could be empty, only just this vertex alone, right, is another rooted tree on one vertex. Here is a rooted tree on this, right? Here is a rooted tree here, just one vertex. Then here is another rooted tree, right? So you can think of these vertices on the path as a rooted tree, and you are putting a linear order on this, right? You are saying that you have to go in this particular order. So it's basically a linear order on rooted trees, right? So vertebrate is basically a linear order on rooted trees. But the linear order is on a non-empty set of rooted trees because if the set is empty, then we cannot talk about this. So therefore, we have a linear order of non-empty set of rooted trees. So we are looking at L plus of A, where L plus is the species of non-empty rooted trees, right? So V is actually equal to L plus of A, right? Okay. Now, we know that the species of linear orders and the species of permutations has the same number of elements, right? When you look at the exponential generative function, they are the same. So therefore, it counts the the number of linear orders on a set and number of permutations on a set are the same, right? It's basically n factorial, where n is the cardinality of the set U, right? So therefore, they have the same generating function, and which means that they are called equinumerous. They have the same number, even though they are not the same. Now there is a one-to-one mapping, right, between them. So therefore, they have the same number. There is a bijection. Therefore, there is the same number of elements. So they are equinumerous. And because of this, if I substitute L plus of A, right, it has the same generating function. So you are substituting A on the same generating function, L plus of A, and S plus of A has the same, same cardinality, right? The species L plus of A, right, and the species S plus of A must have the same number of elements on a set U. Okay, in fact, I should write it as not just this, but this together with some set U, right? Some set U on U or on N, whatever, right? On an n element set or on a set U, then they are the same, right? The cardinality is the same. Now, if you recall, right, when we are looking at this graph, we proved that the permutation of rotatories is basically endo functions, right? Because endo functions can be thought of as like if you look at the map of endo function, we saw that like it basically has this nice structure, right? All the paths on the trees go to a specified vertex, and all these vertices, the end vertices of the trees, right, the roots of the trees, sitting in a cyclic structure, right? So therefore, endo functions are basically a permutation of rooted trees, right? Therefore, S of A equal to N, right? Because it's basically we proved this in an earlier part of the course also. I mean, in the same lecture also, right? I think, yeah. So therefore, S of A is equal to N, right? EN. Therefore, S plus A of A is, S plus of A is equal to N plus, because, look at the non-empty structures, right? If you have at least one element, we can talk about this. So therefore, for N greater than or equal to 1, cardinality of END of N, we know, is equal to N raised to N, right? For any N greater than or equal to 1. And therefore, because of this identity, we get that cardinality of S plus of A is equal to N raised to N for N greater than or equal to 1. But then we know that these two are equinumerous. So therefore, the cardinality of L plus of A is also equal to N raised to N for N greater than or equal to 1. But how did we get this L plus of A? L plus of A we got, this is basically, is a number of vertebrates, right? It is basically the species of vertebrates. But the vertebrate is basically a doubly pointed tree, right? So a tree on n vertex pointed twice. So if it is pointed twice, we know that the number multiplies by n into n, right? N square. So you have n square times whatever was the number of trees on an n element set, right? So A of n. Therefore, cardinality of A of n must be equal to, right, n raised to n divided by n square, which is n raised to n minus 2. So this shows that the number of trees is precisely n raised to n minus 2. So this is another way to prove the number of labeled trees. I count the number of labeled trees. And we wind up with a couple of homework questions. And the first is to show that the vertebrate species can be also thought of as A, the species A, right, of rooted trees plus V dot A. Okay. Now, once you prove this, so to prove this, I give a hint. The hint is that the vertebrate is, as I mentioned before, is said to be degenerate if the head and tail is the same, right? Otherwise, it is non-degenerate. Now, to prove this, you can take the vertebrate and then look at if it is a degenerate one or not. If it is not degenerate, then you can cut off the tail, right? Cut off the tail and then look at the remaining, and then use this as a hint to prove this, right? Then deduce the following, that for n greater than equal to 1, n power n is actually equal to summation k equal to 0 to n minus 1, n choose k into k raised to k into n minus k whole raised to n minus k minus 1. A third question is to show that the pointed species of the product of f and g, f dot g dot, is the product of the pointed species f dot and g plus f dot g f times g dot, right? So f dot times g plus f times g dot. Similarly, show that f composition g dot, this is, I will write it more clearly, f composition g dot is actually equal to f dash composition g times g dot. Okay. Now, prove that f composition x, right? X is the species of singleton, is actually equal to x composition f, which is actually equal to f itself. So therefore, for composition, x is the unit. Okay, I think that is it. So we wind up the short introduction to the species of combinatorial structures, and if you want anything further on this topic, you can look at this book, which is a nice book, Combinatorial Species and Tree-like Structures, by the following people: Bergeron, Lebel, and Leroux. Okay. So if you want, you can refer to this, where there is more details on this, with lots of exercises and also much more advanced topics. Okay, so I will wind up with this for today. See you in the next time.